Hi, in this video, I'm going to discuss relationship between an electric current and a magnetic field. So what is the source for electric force? The source of electric force is electric charges. What is the source for magnetic force? The source for the magnetic force are the North Pole, South Pole magnets. And that has nothing to do with each other, right? The electric charges is electric charges, magnetic dipoles, north and south, north and south. So it shouldn't have any relationship in between. However, though, we discovered that all the substances made of atom, inside the atom, there are electric charges, and proton is in the nucleus and electrons rotating around the nucleus. And this motion of electrons, motion of a charge, produces especially the spin. If you have an amperes electrons, this spin generates the magnetic field, and you're going to have a magnetic field. And such an element is called ferromagnets. Iron, nickels, cobalt, right? So these iron, nickel, cobalts, they have a magnetic domains, and that magnetic domains are from the unpaired electron spins. But before this discovery of all this, we thought magnetic force is magnetic force, electric force is electric force, which makes sense. Shouldn't be gravitational force, is just gravitational force, right? So the professor was doing an experiment to show students that how electric force is unrelated to the magnetic field. But doing this experiment and demonstrating in his class, he actually found that one student said, hey, why don't you change this? And you saw you saw that how electric current, which is the motion, flow of electric charge, is actually generating magnetic field. So here I'm going to repeat that experiment that Professor Orsted was doing. Let's see if I can share that. Okay. I'm going to start with this. Share screen. Here. Yeah, correct one. So here. What's this?
I don't know.
You don't remember what it's called?
Yeah.
Compass.
Compass.
What's the red needle says? Red needle points to?
One needle points to North Pole.
North. And then white one points to?
The South
South. Pole. Okay. Thank you. So something like this. Okay. All right. So it's a compass. So here we have a working compass. Then I have a very simple setup. Using this compass. Right, so I have a compass and just a simple alligator clip, the wire, nothing, and also just AA battery. That's all I have. And here they are helping me out. Right now, the wire is not connected. The screen that you're seeing, the wire is not connected to the battery. So it's just a conductor with free electrons in it, right? And then the direction wire is parallel to the needle that's pointing to north and south. And see what happens if you connect a wire to the battery. Then once you connect it, you're going to have a current flows, right? Flow of electric charge. Then what happens to the compass? This compass feels, so how's the compass works? It's feeling the magnetic field that's produced by the earth. So there is a magnetic field and it's aligning with the magnetic field. But if you have a current nearby, what happens to this compass, which only aligns with the magnetic field? It has, okay, magnetic field. Let's see. Okay, so here we have just a simple setting, wire, alligator clip, and a battery, and a compass. Currently, the compass is pointing north. The switch is not turned on, right, off. And then compass is just pointing to the north. Notice that wire is trying to be parallel to the needle. And then turn on the switch, the current flows. When the current flows, you see how the compass needle deflects. Would you mind doing again? It rotates perpendicular. It points perpendicular to the wire. So you see that when the current flows, the compass needle obviously deflected, as if there is a new magnetic field. And it is true. When the current is produced, current flows, that means it produces magnetic field. The electric current produces magnetic field. And this was a huge discovery that connects that electricity and magnetism. And now we call it electromagnetism. So when you have a flow of a current, which means flow of a charge, if you want to know how the magnetic fields produced, you don't, the direction you don't need to know, but you need to know how it's produced. So that you can use the right hand. I don't know, in the videos, maybe not the right hand. So you use the right hand and you curl up your finger like this, and your thumb is the direction of a current, and all your finger, when you curl up, this is going to be the direction of a magnetic field. And I'm going to show you later how it's produced. But so that when the wire was there, right, like this, and then compass was underneath, so when the current flows, it produces the magnetic field that it goes into this direction. So that's why the needle deflected. And let's see the other one. Okay. Now, let's see this one. So now, I don't know if this is the right one. Let's see, sorry about that. Let's see if I have the right video. 5 here. So instead, I put the wire now in a perpendicular to the compass. And then we're gonna close the switch, then the current will flow. And let's see what happens to the compass needle. Now we're trying to put the wire perpendicular to the compass needle and see what will happen. Turn on the switch.
Nothing.
Nothing happens. Perfect. Right, so this time nothing happens. It's because the compass is already, the magnetic field is already pointing perpendicular to the wire to start with. So I mentioned that the current is going to flow this way. Then underneath the wire, the direction of magnetic field will be like this. You see it? This way. So if you put the compass, if you align the Earth magnetic field in the same direction, you put the wire in the same direction like this, then you don't see the compass deflects. So the professor was initially doing an experiment, make sure that always put the wire, current carrying wire, perpendicular to the direction with the compass. So you don't see anything was changing. And then one time the student said like, oh, hey, how about if you put the compass parallel to the wire or wire parallel to the compass, and what happens? Then the first video you saw, voila, compass deflected. And the student's name is not known, but professor figure out from here the relationship between a current, electric current, and a magnetic field. And so this is called Oersted experiment now. Then I have an interesting too, and that's lastly, I want to show you this video. I believe is this one. Let's see, this is the one. Okay, so again, we put the wire parallel to compass, but what we're going to do now is to reverse this battery, minus plus to plus minus, so then the flow of the current will be reversed. When the flow of the current will be reversed, then the magnetic field, the direction of magnetic field also will be reversed. So please watch carefully the direction of a deflection of needle in a compass. All right, so the wire not connected to the switch right now is parallel to the needle, and we're going to turn on the switch. See, you see the needle deflected completely. How about if we flip the battery? So reverse the direction of a current. Which direction this time the needle will turn? You see it? The direction is now opposite. So I hope you saw that initially it rotated in a counterclockwise and then rotated back. When you reverse the direction, it rotates in a clockwise direction. So the direction of a current also changes the direction of magnetic field that's produced by the current, electric current. I'll show you with the slide here that has the good picture to describe this. Here, this one is the good one, I think. So here, you see that electric currents in a magnetic field. Now you see there is a connection between electricity and magnetism. You might think it's nothing special, but it is a big thing. How can you imagine that? Let's say if there is a connection between a gravitational force and a magnetism, that would be strange, right? So there are two different things that we thought, but it's not. So magnetic field is generated by the current carrying wire. And if you have a straight, so in a picture here, there's a straight current passing through. And around the current, magnetic field is generated by the current. And when you change the direction, reverse the direction of a current, then the direction of a magnetic field also reverses. So they the magnetic field lines around the current carrying wire, straight current carrying wire, is a concentric circle. And as you can see that closer to the current carrying wire, you're going to have a stronger magnetic field. circle, concentric. And then as you go farther away, the magnetic field decreases. Intensity of magnetic field decreases. But these circle, it makes a circular pattern around the current carrying wire. And there is a direction that you can use with the right hand. You put the thumb in the direction of a current carrying wire, and then you curl up your right fingers, and that's going to show the direction of magnetic field produced by the current. And then if you turn it the other way, you see that a magnetic field also, direction of magnetic field also reverses. So it looks something like this. You have a current carrying wire, straight one, and it produces, so in this one, its current is going this way and it turns into this way. But I think in the video you might see flipped. Then what if you make a loop on this current carrying wire, right? Then each segment of this loop is producing magnetic field in such a way, so you can see. Okay, so here's another one that you see the iron filings in here, and you have wire, the conductor connected with the battery power source. Then you have a current flowing. Then when you have a current flowing, these iron filings going to be aligned with the magnetic field, which is actually produced by the electric current. And you see in a picture A, there's magnetic field lines produced by the current, electric current. And let's say now instead of having a straight wire, if you make a loop, how's the magnetic field will be formed? It's going to be formed in the same manner. So imagine that you curl up your thumb along the loop of the wire. So each one of them generates the magnetic field like this. But you can see that, I hope you see that it emphasizes, so the magnetic field will be going inside the loop and comes outside. Inside the loop comes outside. So it becomes like this. So therefore, B, in the picture B, the magnetic field overall, each segment of the current carrying wire is making a concentric pattern like you saw in A. And then when you add up all the segments of the wire, the current, then you see the pattern, the overall pattern of magnetic field looks like that. And this in a picture B. Doesn't this picture look familiar with magnetic field patterns that we know of? How about C, when you increase the number of loops? And overall, each loop makes a pattern, magnetic field pattern like this. And then another loop behind it, below it, also makes a magnetic field pattern like this. So you reinforce certain patterns of magnetic field, and you see the overall magnetic field produced by the several number of loops forms a magnetic field pattern like this in picture C. And we call this as an electromagnet, and I'm going to discuss that in the next video. Let me also do this with the whiteboard. Okay, so now this is the beginning. Strange. So this is the beginning of electromagnetism. Okay. Let me see. Let me hold on for a second. I'm going to stop the video for a moment. the video is here. Okay, so let's go back to the share screen. Okay, so this is what we're seeing is the beginning of electromagnetism. Electromagnetism. Right? In 1820, it's the Professor Oersted. He wanted to show that wire, there's no relationship between electric current and magnetic field. Instead, he discovered, so if you have a current, let's say current is running up to the up, then a compass, if you have a compass on the top like this, they turn. So the compass, when you have a current flowing like this, the compass turns into this direction. And this shows that magnetic field is generated because compass is only sensitive to the magnetic field. It has nothing to do with the electric current. But now it shows that electric current generates magnetic field. And you see that if you have, so let's say this is the current is coming out of the screen. It's a 3D. Then you're gonna have a magnetic field produced like this. This is the direction magnetic field produced. By the way, when you have a mark like this means out of the screen or the page. And when you have a mark like this, it means into the screen. To show that dimension. So this is out of the screen, and then this is into the screen, right? So the circle like this, and then into the screen is the cross. So if you have a current that's going, coming out, then magnetic field is produced like that. If you want to know if you have a wire that's into the screen, then a magnetic field is produced like this. Is the direction of magnetic field. Okay. Then in next video that I'm going to talk a little bit more too, is that instead of having a long wire, now if I make a loop, so the current is, let's see, flowing like this, then you can curl up your finger and you see that a magnetic field has to be, each segment of the loop, it has to be going in like this. It goes in like this, magnetic field. So overall magnetic field, what we're gonna see is by having loop like that, the current, when the current is running, magnetic field be into the loop, coming into the loop, and then coming outside. And yet when you have a number of loops, it emphasizes more, but I guess I'll discuss that again in next video. just to discuss about the electromagnetic coils. And of course, the interesting thing is that when you turn off the switch, so if it's no longer current is running, you still have just a wire but no current, then a magnetic field disappears. When you turn on, the current runs, magnetic field appears. So it's not that it's a conductor or anything, it's that current, the flow of a charge produces magnetic field. Okay, so that's about it for this video. And in the next video, I'm going to talk about electromagnets. See you at the discussion.